Hello. Today I will be presenting my thesis work titled Semantic Understanding for Augmented Reality and Its Applications. Just to provide a quick overview of what I'll be talking about today, I will first cover the motivation behind this project as well as its key contributions, and then discuss the semantic understanding for augmented reality. After that, I will discuss two applications of semantic understanding in an AR context: adaptive augmented reality visual output security and semantically aware meshing. I will then conclude the work and discuss some future research directions. The key motivation behind this work is that a truly immersive augmented reality experience requires a semantic understanding of the user's environment. Some contributions of this work are training an indoor scene semantic understanding model and employing it on a physical AR device, providing a platform on which to build rich AR experiences which utilize the semantic information of a user's environment. In addition, this work explores the use of reinforcement learning for visual output security in AR by training a visual output security policy using reinforcement learning and deploying it on a physical AR device. We also propose the use of semantic context to aid in mesh generation for AR devices. In addition, work on reinforcement learning for visual output security was presented at ACM Census 19 as a demo with accompanying abstract, and the code data and model for the semantic understanding work is available online. Although this work was conducted over a span of 3 semesters, and I'm currently preparing a submission to the Symposium on Edge Computing as a position paper. So now I wanted to talk about semantic understanding in an AR context. So the idea behind semantic understanding, again, is that a rich AR experience really requires an understanding of the user's environment. And so in order to provide a kind of foundation to build these sorts of experiences, I built a pipeline which provides semantic context for AR and employed a system which can overlay a user's field of view with a semantic point cloud. Of course, this is challenging because the system must run in real time while providing high quality results. And AR devices tend to be computationally limited, such as head-mounted specialty devices or mobile devices for mobile AR. And for this purpose, for this exploration, the system was designed to work in an indoor setting, so it can detect objects such as chairs, tables, bookshelves, etc. For this project, Edge servers, a Magic Leap 1, and the Intel RealSense camera were used. An Edge server, or in general the idea of edge computing, is this notion of bringing compute physically closer to the end user to overcome latency and bandwidth limitations. This is particularly applicable to AR because AR devices are computationally limited. And so the idea is that you can bring a more computationally robust server closer to the physical AR device, providing that high compute while minimizing latency concerns. In addition, the Intel RealSense camera was used to capture RGBD frames, and the Magic Leap 1 head-mounted AR device was used to deploy the system. The system architecture is as follows. The Magic Leap 1 head-mounted AR device makes a request for a semantic point cloud to a local edge server. The edge server then runs inference on an RGBD frame to generate a semantic point cloud and sends that result to the Magic Leap 1. The Magic Leap 1 then overlays the semantic point cloud in the user's field of view. In order to accomplish them, a custom mount was built which could mount the Intel RealSense camera on the Magic Leap 1. And this mount was 3D printed in the CoLab. The model which was used for semantic segmentation is similar to SegNet and can take in a 224 by 224 RGB image and segment each pixel as one of 8 classes. Training for that semantic segmentation model was done using the weighted categorical cross-entropy loss function, where the weights were derived using the median frequency method. Here are some example outputs of the trained model. You can see that the model successfully segments out objects such as chairs, pictures, photos, windows, and doors, and qualitatively has relatively high quality results. Here's some quantitative data on the performance of the semantic segmentation model. In particular, the IOU is quite competitive compared to the original SegNet paper, which trained a model on a similar data set. In order to deploy this model on the Magic Leap 1 to overlay semantic point cloud on the user's field of view, 2 things had to be accomplished. One, the two-dimensional semantic segmentation models needed to be projected into the three-dimensional space. Once this was complete, there was some calibration required in order to align the field of view of the Intel RealSense's camera to the field of view of the user. Once this calibration was complete, the semantic point cloud can now be overlaid in the user's field of view. And the result of that is shown here. In this example, the Magic Leap 1's mesh rendering capabilities are used to render the semantic point cloud in the user's field of view, and a custom shader was used to accomplish this. You can see here that the user's field of view is overlaid by information such as where a desk is and where a chair is. Now I would like to switch gears and talk about augmented reality visual output security. Now, the idea behind visual output security is that we want to regulate visual content displayed to reduce distraction and prevent the obstruction of real-world context. We also want to prevent holograms with a lower priority from obstructing holograms with a higher one. And we use reinforcement learning to generate these sorts of visual output security policies through trial and error. Now, the key here is that this type of application requires an understanding of the user's environment. And so if we don't want to obstruct faces and stop signs, for example, we first have to detect those objects. This is why this is an application of general semantic understanding for augmented reality. So here's an example of visual output security. On the left, you can see that the important real-world object is being obstructed by all these holograms. Once the visual output security policy is invoked, the important real-world object now becomes visible. And this is an example from a simulated environment. So the objective of my project was to investigate the feasibility of running these reinforcement learning models on a physical AR device, in this case the Magic Leap 1. And an initial experiment was performed to validate this. Once that was validated, I trained and evaluated reinforcement learning policies for visual output security on a physical AR device. For the deployment, the image tracking library built into the Magic Leap 1 was used to recognize and track an important real-world object, and a couple heuristics were applied. One, we only applied the RL train policy if the hologram's original position obstructed the important real-world object. And once the RL train policy is applied, we move the holograms back to its original position as soon as its original position no longer obstructed the important real-world object. And each hologram, in this case, was treated as an agent. Here's a result of this deployment. On the left, you see that the stop sign is being obstructed by these three holograms, while on the right, the green square indicates that the stop sign is being tracked, and the holograms are moved away from the stop sign to reveal it by the visual output security policy. And there's no noticeable performance degradation during this process. Now I'd like to talk a little bit about semantically aware meshing. The idea behind semantically aware meshing is that meshes are really important for AR experiences because they provide information about surfaces. And this can be used, for example, to place an object on a table. However, mesh quality for current AR devices is not perfect. For example, the Magic Leap 1 mesh can be jagged even for a flat surface and take time and multiple angles to really improve. And so the idea is, what if we use semantic information to improve the quality of meshes? The proposal is to use semantic information to choose the priors and adjust the parameters of meshing algorithms. For example, if we know that a set of points in a point cloud is a surface, we know that it is most likely a smooth plane with sharp edges. Using this kind of semantic context can aid in mesh generation and may speed up the time to generate the mesh quality so that it has the same quality as an algorithm which does not incorporate semantic queue, but can get that kind of quality much faster and with less data. Now I'd like to conclude the work and present some future research directions. I've shown that through semantic understanding for AR, that bringing semantic awareness to AR is possible using an edge server to offload the computationally expensive model, which lays the groundwork for future research that incorporates semantic understanding in an AR context. In terms of visual output security, we show that reinforcement learning models can be deployed without noticeable performance degradations, and our full paper and more detailed results also have more specific results on the types of models that make the most sense for this application. Finally, semantic context has the potential to aid in mesh generation. In terms of future work, I believe that semantic understanding of a scene can be used for more AR applications, and that we can investigate more robust semantic models for this sort of application, but there's a limitation of real-time performance, which really makes this an interesting problem. In addition, I think we can incorporate SLAM and semantic information to build a so-called reality map to bring richer experiences to augmented reality. In terms of visual output security, I think deciding what objects are considered important in a visual output security setting is not trivial and probably depends on a user's context and needs to be investigated further. And in addition, non-visual output security concerns should also be considered, such as haptic security or audio security. Further, I think that we can apply RL to other applications in AI, which is an exciting future direction of research in itself. And finally, I think we should build a mesh generation pipeline which is aided by semantic cues to validate this idea of a semantically aware meshing algorithm. Thank you.